Hi, kiddos. So this is your AP Environmental Review Part 2. We're going to quickly go over the math that you needed to learn throughout the course of the year. So the first thing that we really need to talk about is scientific notation. So why do we use scientific notation? It's used for a variety of reasons. The three big ones are to show really large numbers, really small numbers in an easier format. The second reason is to make doing math a little bit easier. So if you have all those large numbers or very small numbers, looking at them and doing calculations or operations using those numbers can be a challenge. So it can simplify things. And then the third reason is because we need to show proper accuracy of our measurements. So if you remember, accuracy was how good your tool was. So you need to properly show that with the right number of significant digits, and scientific notation helps us do that. Okay, so to write scientific notation, the number has to be between 1 and 10. And then you multiply it times 10 to some exponent. Okay, and the exponent tells you where the decimal place is. If it's a larger number originally, when you convert it, it's going to have a positive exponent. If it's a smaller number originally, it's going to have a negative exponent. So if I had 200, let me get down here, 256, and I was converting that into scientific notation, I need to change this number into a number that is not, that is between 1 and 10, so I would convert it to 2.56, and then I need to tell the person who's looking at it how many times I had to move the decimal point to get it there, and that would be times 10 to the 2. If my number was 0.00000590, then I would take my significant digits, which would be the 5, 9, and 0 here at the end, and I would convert this to 5.90. So I'm changing it into a number between 1 and 10, and times 10 to the, and I moved it 1, 2, 3, 4, 5 spaces. You're gonna have to bear with me with my cat scratches here, getting used to a new stylus. I appreciate your patience. If you were adding or subtracting scientific notation, you first have to make sure that you have the same exponent. You transfer the smaller value exponent into a larger value exponent by moving the decimal on the original number, and then you just go ahead and add the two numbers, and the exponents end up saying the same in the answer. Whereas if you're multiplying or dividing, then you don't have to change the exponent. You just multiply or divide the original number and then add for multiplication or subtract the exponent with the 10 for division. Okay, so for here, 1,000. Oh, maybe it's not. Yeah, there we go, 1,000. Okay, so it would be 1 times 10, and then how many spaces did we move? 3. And then here, similarly, we have 256,000. So we would, oh, I lost my marker. Okay, we would write 2.56 times 10, and then 1, 2, 3, 4, 5 times 10 to the 5th. Okay, do the following calculations in scientific notation. Once again, we're looking at an exponent of 7 and an exponent of 8. So how are we going to change this to an exponent of 8? Well, in order to do that, we have to move the decimal place over as if we had moved it over 8 places instead of 7 places. So here we moved it over 7. Here we would have moved it over 8. So we were going to convert this number to to 0.296 just want the decimal, there we go, times 10 to the 8 and 1.0 times 10 to the 8th. And that would then give us, if I add those together, 1.296 times 10 to the 8th. And then our last one down here, we have 500 billion times, let's see if I can get this. So 500 billion, so 500 billion would be times 10 to the 9th, so billion is times 10 to the 9th, but it's 500 billion, so if I change that 0.00 to true scientific notation, that'd be times 10 to the 11 times 35,000. So now let me convert that really quickly, 35,000, and I'm going to convert that, and that's going to be 3.5 times 10 to the 1, 2, 3, 4 to the 4th. And since we're multiplying, we're going to multiply these first two numbers, 5 times 3.5, and then we're also then going to add the exponents. So let me get down over here. Okay, so 5 times 3.5. If I calculated that out, please remember that you won't have access to a calculator, so you'll have to be able to do this. But 5 times 3.5 is 17.5. So that's going to give us 17.5. And then 17.5 times 10 to the, and then I'm adding them 10 to the 15, right? So my exponents added together, but now this isn't quite right. I got to move this over one more time. So I have to add one more exponent here, and I'm going to end up with 1.75 times 10 to the 16. All right. In these conversion problems, you are going to be looking at converting using the metric scale. And so I'm not going to tell you the metric scale. You need to have it memorized from giga to nano. And there are many tutorials on that, so I'll let you explore that if you still need help with it, or you can contact me privately. But here we're looking at 1200 watts, and we're changing that to kilowatts. So we're going to be moving left on the metric table, and if you're moving left on the metric table, then your decimal point moves left. We're going to be moving from basic unit left 3 spaces. So we're going to go 1, 2, 3, and that's going to leave us with 1.2 kilowatts. On this one, we have milliliters transferring to liters. We're moving once again left on the metric scale, 1, 2, 3, 4 spaces. So ours is going to, we're going 1, 2, 3 spaces. So that should be 14 liters. So just to remind you of some different energy concepts. Energy is basic, the basic unit of energy is a joule. There's other units that we use, sometimes calories or kilocalories, which you see in the back of packages. You can use kilojoules, you can use the British thermal unit, and you can use therms. However, the conversions are down there. You don't have to have the conversions memorized. They'll give you this type of conversion calculation. But I do want you to remember also that power, or things in watts, are energy over time. And so 1 watt is equal to 1 joule per second. And this practice problem right here is a little bit more complicated than you're probably going to see on the AP exam. But I just wanted to kind of make you aware of what a dimensional analysis like this might look like. So in this case, I've got 1,000. Let's see, 1,300, oh, sorry about that, 55. And that's, this is a struggle, kilowatts, hours. So I'm going to do my little dimensional analysis. I call it factor label method. In this case, you've got 1 joule per second. Oh. And then we also know that that is equal. So 1 joule per second, our conversion factor there is 1 watt. So, oh, I don't know what happened to our second there. I'll put it back. Okay. And so then we know that we have 1 watt is equal to, oh, just kidding. We have 1,000 watts. 1,000 watts is equal to 1 kilowatt. And then we have 3,600 seconds is over 1 hour. Okay. And so now I'm going to double check that I've crossed everything off here. So I've got here, I've got my kilowatt hours. So I've knocked off kilowatts. Oh, I've knocked off kilowatts here. I've knocked off hours here. So you can cross that out. I've got joules still here. I've got watts here. That crosses out. I have seconds here. That crosses out. So the only thing that I'm left here is with joules. And that's what I was trying to solve for. I was trying to solve for joules. So if I multiply that across the top, I have 1,355. 1,355 times 1,000 times 3,600. And everything is 1 at the bottom, so I don't need to divide by anything. And I end up with, over here, come here, 4.88 times 10 to the 9th. That's not in kilowatt, in kilojoules. That's in joules. So I know that if I need to convert that to regular, to kilojoules, then I need to move the decimal place over 3 places, or that would be 4.88 times 10 to the 6th joules. So we're going to change this to turn it into kilojoules. And so 4.88 times 10 to the 6 kilojoules. So based on what we had before, we had 4.88 times 10 to the 9th joules per day, and we have 30 days. Oh, sorry, that's joules per day. And in order to get that day to disappear, we're going to multiply by days. And once again, these are going to cross out. Oh, 30 days. So we end up with, I notice that I'm using joules and not kilojoules. So I end up with 1.46 times 10 to the 11. Okay. And then at the rate of 0.0749 kilowatt per kilowatt hour, what will your electric bill be for the month? And so let's look at this. We've got 1,355 kilowatt hours. And we know that it's 0.0. Sorry about that. Let's see if I can find it. 0.0749 times, that's a 9, per kilowatt hour. And this is probably about as hard as your dimensional analysis will be. And then you're going to multiply across the top. So this is over 1. Multiply across the top, and you end up with $101.49. Awesome. Okay, so if you're to look at this, don't forget that the formula that you need to have memorized is ending minus starting over starting. The AP exam will not provide your formula. So in this case, we have 240 parts per million going to 360 parts per million. What is the percent increase? And so for this question, we're going to do 300. Oh, let's see if we can get this not to feel crazy. 360 minus 240, and we're going to divide that by 240. Oh, look, I'm getting better at this. Yeehaw! All right. And so you end up with 120 divided by 240. So that is equal to 1/2, or 50%. Okay. So in this problem, we're doing percentage growth rate. If you remember, you're going to have these calculations memorized as well. So in this case, we're trying to solve for R, which is growth rate. So R is equal to 100,000 plus 30,000. And then that's going to be multiplied. Subtracted from the combined amount of loss here. So we've got 70,000 deaths and 50,000 immigrants, which is exit, right? So 50,000. And then that whole value is put over the total original population. So that's 5 million. And so if we calculate that out, R is going to equal 0.002 or 2%. And then if the country has a growth rate of 1%, how many years will it take for the population to double? Remember that rule of 70 and you just use percents. And so it was the 70 over the growth rate, right, is equal to the doubling time. So if we do 70 over 1%, and remember you use percents in this, you don't convert it to decimal, then that is going to equal 70 years, and it's going to be doubled, right? That's a pretty big deal. So for half-life calculations, I like to be a little bit more intuitive, and so I am going to go over this, how I would solve it in my head without using the crazy formulas or calculations. I feel like you already have enough to memorize. Okay, so a sample of radioactive waste has a half-life of 10 years and an activity level of 2 curies. After how many years will the activity level be 0.25 curie? You don't need to know what a curie is. You just need to know you're going from 2 curies down to 0.25 curies. So let's just look at what that might look like. We've got 2 curies, then we have 1 half-life, and then we'd have 1 curie, then we'd have 1 half-life, and then we'd have 0.5 curies, then we'd have 1 half-life, and we'd have 0.25 curies, right? So how many half-lives do we have? We had 1, 2, 3. How many years are each of those? 10 years. Okay, so then that means that was 30 years. So just a reminder that the way to measure primary productivity or gross primary productivity is gross primary productivity, or the total productivity by the primary producers minus the respiration, so what they use up to grow and live, is equal to the net primary productivity. And that's what's actually available to the next trophic level. So that's why this equation is important. So if you look here, the net annual primary productivity of the wetland is found to be 2,000 kilocalories per meter squared, and the respiration is 18,000 kilocalories per meter squared, then what is the gross annual productivity? So really what we're looking at here is we're looking at, oh, come on, baby, GPP minus R is equal to NPP, and this is 2,000, and this is 18,000, and we're solving for this right here. So we're going to add 18,000 to both sides, and that's going to give us 20,000. I've been a little bit lazy with my units, so let me look up here. Oh yeah, I've got kilocalorie per meter squared per year. And so that is my GPP. In this calculation, we're just looking at the transfer of energy. And so we've always said that the average transfer of energy between trophic levels is about 10%, but that's not always absolutely true. And so they're looking at a specific ecosystem and the transfers, and they're trying to calculate the percent transfer to the next trophic level. Okay, so we have producers to primary consumers. And so if you took, I'm having a hard time getting the tablet down here, 1,800 divided by 9,000. So 18 was transferred out of 9,000. And so that would be 0.2 or 20%. So the LD50 is the lethal dose where half of the organisms die at that particular dosage. And so the LD50 for aspirin is 200 milligrams per kilogram with rat taken orally. So how many milligrams of aspirin would it take for for 50% of children to die? If it was a typical 1-year-old toddler size, so about 10 kilograms. All right. And I know it's morbid, but this is really pertinent. So you've got 200 milligrams per kilogram for the rat, and then you've got 10 kilograms of child, and you want to know how many, milligrams. So we're going to multiply across. Once again, this is the dimensional analysis, and you end up with about 2,000 milligrams. And since each pill is about 500 milligrams, then it could be as little as 4 pills in order for it to be lethal to half of a 1-year-old toddler population. So that's why you have to be so careful as a parent, and we have those child safety tops. All right, math geniuses, we're almost there. So I want to just thank you for your patience. So here, you're just saying use the graph to calculate the LD50 for rats with cesium. And so on the bottom of the graph, you have your cesium dosage. On the y-axis, you have the number of dead rats. And so you have a 50 total rats. So half of them dying would be this number 25. You carry that across. That's like right there, right? Let's see if we can mark that. And then we're going to, oh, that was a really bad line. We're going to bring it down here. So we're looking at somewhere like between 2.6 and 2.8 in there. So if you said like 2.75 or 2.7, anything between 2.6 or 2.8 would probably be okay on the AP exam. And that would be acceptable. So what is the threshold on the graph? And the threshold is that value where you actually start to see death. And so we're looking at this value right here, and the value for that is 1.5. You have stuck with me really, really well, kiddos. I'm so proud of you, as always. Keep working hard. And if you need additional help with some of the additional problems, don't forget that I've got